This case study, demonstrating how design of experiments was used to understand and control the output of a wastewater treatment facility, is brought to you by JMC Data Experts. Wastewater from a massive glass and metal machining facility is chemically treated and sent to settling tanks to remove suspended solids. Environmental engineers measure the turbidity of the outgoing effluent, which cannot exceed 15 NTU units, or an EPA notification must be issued. Turbidity levels seem to move with a mind of their own, and the facility needed to find a way to control the turbidity of the output from their wastewater treatment facility. Design of experiments is a systematic method to determine the cause and effect relationships between input and output variables in your process. Not only is it the most economical way to learn those relationships, but it also provides a mathematical model of your response, which can be used to predict and control process outputs. The process mixed the wastewater with a flocculant and a surfactant before sending it to a settling tank for the solids to settle out and the clarified wastewater to be sent to a local stream. Noise variables such as the wastewater flow rate, solids content, and cutting oil concentration were thought to make the process too unstable to control or understand. The question remained, which inputs were causing the variation in turbidity? Historical data was used to dispel some myths about the causes of turbidity upsets. For example, concurrent time series plots of flow rate and turbidity made it clear that the two were not related. Digging deeper into the possible input variables was important as well. For example, wastewater pH was not considered important until the chemical supplier's chemist suggested it should be studied. The experiment design focused on the chemical treatment of the water without considering the noise variables from the production process. The logic was that if we could not make it work on a lab bench, we would have no chance in the highly variable plant floor. A 2 to the 3rd full factorial design centered around current process conditions was used. It was replicated twice to improve the power of the experiment. The results were surprising, but not uncommon. The half-normal plot of effects shows that only the pH in the flocculant had a significant effect on turbidity, but the surfactant did not. We say not uncommon because the pH 4110 interaction was key. One of the strongest reasons for using factorial designs is that they discover predictor variable interactions that have a major impact on the response. Here we see the interaction graph for pH and 4110. If 4110 is used at the high pH, the turbidity remains relatively high. There is no effect. Increasing the flocculant, which should lower the turbidity, only does so if the pH is low. In the past, surfactant additions only helped lower turbidity because it is mildly acidic and lowered the pH. The new process took advantage of this interaction by first lowering the pH of the wastewater and then adding the surfactant and flocculant in the mix tank. The new process had little trouble staying below the EPA limit of 15. Also, the amount of the expensive surfactant was reduced dramatically because the low pH was the key to getting the process to work, not the surfactant itself. Cost savings from using less surfactant were about $46,000 per year. If you would like to use design of experiments to understand and control your problem processes, or if you have a question about this case study, contact us at JMC Data Experts.